Have you ever looked out at the ocean and seen one of those enormous drill ships, or maybe a massive construction vessel, and just wondered how it stays so perfectly still? It's kind of mind-boggling, right? You've got wind, waves, currents all pushing on it, and yet it just holds its position, almost like it's frozen in place. Well, the secret behind this incredible feat is some truly brilliant engineering. So yeah, how do they pull that off? I mean, how does a ship that weighs tens of thousands of tons hold its ground against the full raw power of the ocean? It's not magic, and it's definitely not some giant anchor. The answer is a pretty amazing technology called dynamic positioning, or DP for short. The best way to think about it is like a super smart, totally automated brain for the ship. It's constantly sensing the forces of the ocean and then making these tiny, precise adjustments to all its thrusters and propellers to cancel them out. Okay, so to really get how this all works, we first need to dive into the tools that the DP system has to play with. So take a look at this. This is a pretty typical DP-equipped vessel. All those propellers, thrusters, and rudders you see, you can think of those as the muscles. And here's the key. No single one is in charge. They all have to work together, in perfect harmony, pushing and pulling to keep the ship exactly where it's supposed to be. And what is the system trying to control? Well, it all boils down to these three basic movements, or what engineers call degrees of freedom. You've got surge, which is just moving forward and backward. Then there's sway, which is sliding from side to side. And finally, yaw, which is basically turning or rotating. The DP system's one and only job is to create the perfect counterforce to stop any unwanted movement in any of these three directions. Now, this sounds pretty straightforward so far, right? But this is where it introduces a fascinating and, believe me, an incredibly complex problem. So a typical vessel might have, say, 7 different devices that can create force. Engineers call these actuators. We're talking main propellers, tunnel thrusters up in the bow, and those cool azimuthing thrusters that can spin a full 360 degrees. But remember, we only need to control 3 things. That's surge, sway, and yaw. And here's the crucial point. With 7 tools to do just 3 jobs, the system is what's called over-actuated. And this means that for any given situation, there isn't just one right answer. There are, mathematically, an infinite number of ways to combine thrust and rudder angles to get the job done. You could do a little push here and a big one over there, or maybe a few medium pushes from different spots. They could all add up to the exact same result. So you can see the challenge this creates for the computer, right? Out of an infinite number of correct answers, which one is the best one? How do you even begin to define what's optimal? Well, engineers define best based on a few really key things. First, you want to use the absolute least amount of power possible. That saves fuel. You also want to avoid those sudden, high-power bursts of thrust that really strain the equipment. You definitely don't want your rudders and thrusters constantly wiggling back and forth, because that causes a ton of wear and tear. And above all, you always have to prioritize control over the ship's heading. It's yaw. To find this one best solution, they use this really elegant idea called a cost function. It's basically a formula that takes any possible combination of thruster outputs and gives it a penalty score, or a cost. A solution that guzzles power, high cost. A solution that makes the thrusters jitter, high cost. The goal, every single second, is to find the one combination that has the lowest possible cost. And the go-to tool they use to solve this puzzle, to find that lowest cost solution in a split second, is a powerful mathematical method called a quadratic program, or just QP for short. It's literally designed for exactly this kind of optimization problem. So, problem solved, right? We've got a perfect mathematical tool to find the perfect solution every single time. Well, not quite. This is where the clean, orderly world of math smacks right into the messy, chaotic reality of the real ocean. And you can see the disconnect right here. On one hand, the goal of that QP formula is smooth, stable, efficient control. But what can happen in the real world is, well, a lot of undesirable stuff. You get fluttering rudders, thrusters that are constantly rotating back and forth, and this kind of general unwanted oscillation as the system hunts for the perfect answer without ever really settling down. You can actually see that instability here. Instead of a nice, smooth, stable line of output, you get this constant wavering. And that's because the pure mathematical formula doesn't really have a cost for tiny, rapid movements, so it doesn't try to avoid them. This doesn't just waste energy, it puts a huge amount of stress on the machinery over time.
So the research paper we're looking at highlights several of these weaknesses. For example, in really calm seas, the rotating thrusters can just spin around needlessly. The system also struggles to handle what are called spoil zones, basically forbidden angles where a thruster might blast water into the hole or mess with another thruster. And when you try to add in other real-world limits, like a total power cap for the whole ship, the math gets so complicated it becomes almost impossible to solve in real time.
And this wild-looking image, this shows us why. When you start piling on all those real-world constraints, the map of possible solutions becomes this incredibly complex, multi-dimensional shape. Trying to pre-calculate the best solution for every possible point on this map is, as the paper calls it, a computational nightmare. So if the pure math solution has these real-world problems, what's the answer? Well, this is where the researchers proposed a much smarter, more practical, hybrid approach.
And they say it right here. The new idea isn't to just throw out the powerful math, but to combine it with other strategies. It's a hybrid system that blends things that are calculated beforehand with things that are adjusted on the fly.
So their algorithm is clever. It basically runs 3 different strategies all at the same time. Solution 1 is a simple, pre-calculated plan where the thrusters are mostly in fixed positions. Solution 2 allows for some limited rotation, and Solution 3 is that fully flexible, pure math approach. But the real secret sauce is a smart algorithm that, for each and every thruster, blends these 3 solutions together in real time to get the best result without all those nasty side effects. And by doing this, the system really gets the best of both worlds. It has the speed and the stability of those simple pre-calculated solutions for when the seas are calm, but it keeps the power and the flexibility of the complex math for when the weather really gets rough. It's just a more robust, efficient, and practical way to solve the problem. You know, this whole story is just a fantastic example of how an elegant, theoretical solution has to be adapted to work in the messy real world. It really makes you wonder, doesn't it? As we move towards fully autonomous ships, what other perfect solutions out there are going to need a serious dose of reality? And what new computational nightmares will engineers have to solve next?